The fifth video on A-level trigonometry looks at radians. So a reminder, these videos are aimed at students doing A-level courses in mathematics or equivalent courses where you're aged around 17 to 18. This particular video is going to look at questions which involve radians, and some of the questions are going to be quite similar to the problems covered in videos 2 to 4, but we're going to use radians rather than degrees. First then, we need to know what radians are, and we need to emphasize that as you get older, you'll find that people tend to use radians in preference to degrees, and there are many reasons for that, which we won't go into here. So first of all, what is a radian? Well, it's just a different unit. So you could say going from degrees to radians is a bit like going from centimetres to inches. It's just a different way of measuring the same thing. So all we need to know is what the equivalences are. So you can see 0 radians is the same as 0 degrees. If you have 45 degrees, that is pi over 4 radians. If you have 90 degrees, that's pi over 2 radians. 135 degrees, 3 pi over 4 radians. 180 degrees, pi radians, and so on. So what's the simple translation? What you'll notice is the key one to remember is that 180 degrees is the same as pi radians. So to go from degrees to radians, you multiply by pi over 180. But to go from radians to degrees, you multiply by 180 over pi. And that's really all you need to be familiar with. Now for completeness, it might be useful to sketch a graph. So what I'm going to do here is I'm going to first of all put some degrees onto this graph. And I'm going to say, alright, let's sketch a sine curve. So a sine curve on this sort of scale looks like that. Now what you need to be able to do is say, okay, what would it look like if I did it with radians? Well, 90 degrees is pi by 2 radians. 180 degrees is pi radians. 270 degrees is 3 pi over 2 radians. And 360 degrees is 2 pi radians. And really, that's what you need to be familiar with. So if I sketch a typical curve like sine, can I represent it in radians instead of degrees? And you can see that the conversion is fairly straightforward. I could of course do a cosine curve, which looks something like that. So there's my cosine curve, and I could of course also do a tangent curve, which is going to look something like this. So I'm not brilliant at the tangent, but you get the point. Alright, so that's the key thing. Can you represent your trigonometric curves using radians rather than degrees? And you'll notice the key point, I just changed 90 degrees to pi by 2, 180 degrees to pi, and so on. Some questions then. Find a single solution in radians for the following problem. And what I'm suggesting is, first of all, before you start, just remind yourself of this key fact, that 180 degrees equals pi radians. So 30 degrees must be equivalent to pi over 180 times 30 radians. And obviously that gives me an answer of pi by 6 radians. So that was a relatively straightforward question. Next one then, find a single solution in radians for the following. Tan theta is minus root 3, or it's telling you the answer there is theta is 120 degrees. So again, we just start from my key fact, and we say to go from degrees to radians, you multiply by pi over 180. So I'm going to do 120 times pi over 180, which gives me 2 pi over 3. So there's some easy questions to get started, and now we'll go to some slightly more challenging ones. Find the solutions in radians for the following expression in the domain 0 less than or equal to x less than or equal to 2 pi. And as in the earlier videos, what I'm going to recommend is you first of all do a sketch of a sine curve. Now, you're probably a lot happier doing a sketch of a sine curve in terms of degrees, but this question has asked for radians. So what I might do is first do the sketch in terms of degrees, and then simply write on it, okay, 0 degrees, 0 radians. 180 degrees, pi radians. 360 degrees, 2 pi radians, and so on. So just overlay the radians on the same curve so that when you need them, you can see where they are. Now, having done that, I now get on with the question. So if we want to solve this, 6 sine 3x minus pi by 4 equals 3 root 2. That's the same as saying sine 3x minus pi by 4 equals 3 root 2 over 6, which hopefully you can see is 1 over root 2. So the next thing is you're saying, okay, where can I see 1 over root 2 on my graph? Well, 1 over root 2 is going to be roughly here. So you can see you've got a solution here, a solution here, a solution here, and a solution here. Now, I happen to know that if you get 1 over root 2, you're talking about 45 degrees, or in radians, pi by 4. So what you've actually got is 3x minus pi by 4 equals pi by 4, that's that solution there, or 3 pi by 4, and that's that solution there. And you remember the solutions always came in pairs. Now, of course, you can see there's other solutions further on. There's another pair up here. So if I want to get that pair, you notice I add pi to the original ones. So I'm going to get 3x minus pi by 4 equals, so I can have pi by 4, 3 pi by 4, that's the first two, and then I add pi to each of these, so I 2 pi to each of these. So I'm going to get 9 pi by 4, or 11 pi by 4, and so on. Now I'm going to stop there. There could be more that I need, and if I need more in order to solve this, I'll go back later. Now I'm going to subtract the minus pi by 4, so I get 3x equals 0, pi by 2, and then you'll see the next one is just going to be 2 pi, and the next one's going to be 5 pi by 2, and so on. And then finally, of course, what that's going to give me is x equals 0, pi by 6, 2 pi by 3, 5 pi by 6, and the next one is going to be beyond 2 pi, so I won't need it. Next question then. Find the solution in radians for the following. Tan squared of 2z plus pi by 3 equals 3 in the domain 0 less than or equal to z less than or equal to pi. So again, I'm going to start by doing my sketch. There's my tan curve, and because this question is in radians, first of all, I'm going to convert all these numbers to radians. So 0 degrees is 0 radians. 180 degrees, which is roughly here, is going to be pi radians. Minus 180 degrees, which is roughly here, is going to be minus pi radians. And if you wanted to mark the asymptotes, the asymptote, for example, is at pi by 2 and minus pi by 2. So I can overlay on my horizontal axis the angles in radians, so I can see them when I need them. Right, what am I going to do next? First of all, I have to solve this problem. So what I've got is tan squared of 2z plus pi by 3 equals 3, which tells me that tan of 2z plus pi by 3 equals plus or minus root 3. Now it's important you remember to put in the plus or minus, because we're doing a square root and it could be either. And then we do our normal trick. We say, okay, where does that appear on our graph? Well, root 3 is up here somewhere. So if I go across, you'll see I've got a solution here, solution here, solution here, and so on. And minus root 3 is down here. So again, if I go across, you see I've got a solution here, solution here. So I can see where my solutions are. Now, if you put this into your calculator, you'll find that root 3 corresponds to plus 60 degrees, or pi by 3, and minus root 3 corresponds to minus 60 degrees, or minus pi by 3. So what I've got is 2z plus pi by 3 equals pi by 3, that's for the plus 60 degrees, and 2z plus pi by 3 equals minus pi by 3, and that comes from the minus root 3. And then of course you see that the differences between solutions are pi. I always step by pi, which is equivalent to 180 degrees. So I could have pi by 3 or 4 pi by 3 or 7 pi by 3. And similarly, I could have minus pi by 3 or 2 pi by 3 or 5 pi by 3, and so on. Now what I can do is I can move the pi by 3 I've got here on the left over to the right. So if I do it for both lines separately, I get 2z equals 0, pi, 2 pi, and you can see the pattern on that top one very quickly. And for the next line down, I get 2z equals minus 2 pi by 3, or, and this one's a bit more tricky, so I need to be careful here. So 2 pi by 3 minus pi by 3 is just pi by 3, and then 4 pi by 3, and so on. And of course, finally, I can now solve for z. If I can just about squeeze that in. So I've got z equals 0, pi by 2, pi. That's all I need from the top row, and for the one below, I don't need that one because it's negative. So I then get pi by 6, 4 pi by 6, and the next one would be up beyond the domain that I need. Question 5 then. Find an equation for the following curve given the coordinates of A are 0, 5 pi 6, B 0, 17 pi over 6, and C are 29 pi over 6. And you're going to need to decide whether you want to use sine or cosine for this, but it will probably be fairly obvious which is easiest once you start. Now, the first thing I'm going to do is notice this point A is at 5 pi by 6, but a point that I know quite well is obviously just pi. So what I'm going to do is I'm going to mark a line. Oops, I've not quite got that in the right place. That does happen sometimes. So I'm going to mark a line down here and say that corresponds to pi. Similarly, if you look at the point B, which is 0, 17 pi over 6, then I could mark a line 3 pi. So I'm going to do that here. There's a line 3 pi. And if you wanted to, you could see, of course, there's a line that corresponds to 2 pi. And similarly, if you wanted to, you could mark down a line here which corresponds to 0. Now the reason I've done that is by putting on these things on the horizontal axis, it gives me a better indication of what's going on. Now the next thing I'm going to look at is what's the gap between my points. So what's the gap from here to here, and what's the gap from here to here? So if I go from A to B, then what you'll find is the gap is 12 pi by 6, or 2 pi. If I look at B to C, then the gap is also 12 pi by 6, or 2 pi. So what you can see is a change in x, so if I write this as the x-axis, of 2 pi gives half a period. So if you look, as you go from A to B, you can see you've got half a period of a sine or a cosine. So what that's telling you is if, for example, you plotted sine of alpha x, and you put in the values of x from A and x from B, then you're saying if x goes through 2 pi, then alpha x goes through pi. So that tells you that alpha equals a half. Okay, So we've now worked out what the period, the frequency is for our curve. So next what I want to do is overlay a curve of the same frequency but make it a pure curve. So what I'm going to do, you can choose for yourself, but having seen where that 0 is, a logical curve to choose is probably going to be a cosine, because a cosine starts at 1 when the angle is 0. So if I was to do a cosine curve, then I'm going to get something that looks, I'm not a good sketcher. You're going to get something like that. So what I've just sketched is cos of x over 2. And you can see that cos of x over 2 is quite close to the curve that I've got. And now you're going to ask yourself, alright, what's the relationship between the curve I've got and the curve that I actually want? And you'll see that there's a shift. Basically my cosine curve is shifted to the right by pi by 6, or alternatively you could say that the curve I'm trying to match is shifted to the left by pi by 6. And we all know, hopefully, your formula with shifting. So what we don't want is cos x over 2. What we want is cos of a half x plus pi by 6, and that's going to give me my actual curve. That's the magenta curve. And that's just to remind you of the key things you need to solve trigonometric questions. You need to understand the relationship between degrees and radians, and you need to understand the periodicity of the sine, cosine and tan curves.